Well, hello there again. After our excitement on 2-3A, you guys are so very patient with me when we were having those technical difficulties. I figured out that there was a network issue going on campus, or at least with my iPad, that wasn't allowing me to share. So I've got that figured out now, so hopefully that won't happen again. But thanks again for being gracious and flexible as we just kind of worked on the fly. For 2-3B, I'm going to introduce you to two more rules for derivatives. Each rule we learn will allow us to work with different types of functions. So we're going to learn the product rule today and the quotient rule. So these are rules that deal with products that are a little bit more complex than the functions we saw in 2-3A. So here's the product rule. U stands for an entire function. Sometimes you'll see U isn't just a variable. U represents some kind of f of x. So it could be a long polynomial, a parabola, a cubic, a square root. U is some function, and V represents a different function. Okay, so two completely different functions that are multiplied together in the same problem. And the rule for the derivative is as follows. You use parentheses, all right, and it would be U multiplied by V prime combined with V multiplied by U prime. Okay, did you get that? So it's a combination of each. It's one regular with one derivative, and then the combination of the opposite regular with one derivative. So you might see it written this way: the derivative of f of x times g of x, if it's a product, then that would start with f of x times g prime, and then g of x times f prime. It helps if you actually see it in practice. The derivative of a product is actually the sum of two different products, right? And those two different products are a combination of one derivative and one original function. So here's a real basic, simple one. This is our f of x, or our u function, and this is our g of x, or our v function. So if we want to find df dx, which is the first derivative, then we need to follow the rule for u first, followed by v prime, plus v first, or followed by u prime. So the u function is 2x minus 1. V prime is the derivative of the second part, which is just 3, because it's not a power function, plus the v function, which is 3x plus 4, times the derivative of the first function, which again, because it's not a power function, is just 2. We use distributing to clean this up a little bit, so we'll have 6x minus 3 plus another distributing, so 6x plus 8. And so we're looking at an overall value of 12x plus 5. And that is the derivative using the product rule of two very simple functions. Here's another product rule opportunity. These are a little bit more complex. We have a cubic and then a quadratic. So a power 3 multiplied by a power 4. So let's find f prime. And we'll start with f of x times g prime of x. And we'll add to that g of x times f prime. So following the product rule. So f of x is x cubed minus 4 times g prime, because it's an x squared, then the power rule tells me that's 2x plus 0. Now I don't need the plus 0, so I'm just going to say it's 2x And then g of x, which is x squared plus 3, and then times f prime, which is the power rule 3x squared minus 0. And again, the minus 0 is unnecessary. It's redundant or an irrelevant piece. All right, so that is the setup for the product rule. Now it just becomes the cleanup where we're going to do distributing. And we'll distribute into each term. So we'll end up with 2x to the 4th minus 8x plus 3x to the 4th plus 9x squared. So combining like terms, we end up with 5x to the 4th plus 9x squared minus 8x. You could also write that with a common factor of x taken out, and 5x to the 3rd plus 9x minus 8. There's not a real advantage to doing that this way. You could leave it in either one of those forms and either one would be acceptable. I would probably stop here unless I was going on to do something more with this, like finding horizontal tangents or something, but for just finding the derivative, you could probably stop in the polynomial form. That leads us to rule 6. So what do you do if you have a quotient? So you've got one kind of function on the top and one kind of function on the bottom. In other words, you're looking like you've got an f of x on the top and a different g of x on the bottom. And if you want to take the derivative of that, how does that rule go? So for a quotient, it's backwards. Instead of starting with u, you start with v. And then you have u prime. And because it's backwards, it's minus. And then we have u and v prime. So the pairing, the idea of pairing one derivative and one non-derivative is similar to product rule, but you've got to watch the order here. You've got to make sure you start with the base function, the bottom function. And then the other difference is that this has a denominator to it, and the denominator is the v function squared. Now there's a big proof to the quotient rule, which we're not going to cover in the scope of our class. If you want to Google it or look it up, it can be there, but I'm just going to tell you what the quotient rule is, just like I told you what the product rule is, and we'll save a proof for another time. So just want to emphasize, order is important. So make sure you set that up, especially the numerator, that it goes in the right order. So we're going to apply the quotient rule to this question. The top would be our f of x. The bottom would be our g of x. So if I'm finding the derivative, then I have to start with g of x first, and then I'll multiply by f prime. And then I will subtract f of x, and I'll multiply that by g prime, and the whole thing would be over the g of x function as a quantity squared. So I'm going to start with the g of x function, which is x squared plus 3, and multiply it by the f prime, which with the power rule is 3x squared minus 0, but the 0 is negligible, minus, and then f of x, so x cubed minus 4, multiplied by g prime, which is 2x. And this whole thing would be over the quantity x squared plus 3 quantity squared. The good news is that you don't have to simplify the denominator. You leave the denominator as a squared quantity. There's no need to FOIL. Okay, we just want to leave that alone. The numerator, however, we should distribute and simplify. So when I distribute the numerator, I'm going to have 3x to the 4th plus 9x squared. And when I distribute the second half of the numerator, including the negative sign, don't forget, So I'm going to have minus 2x to the fourth plus 8x. All right, so I've got a double negative going on there, all over the quantity x squared plus 3 quantities squared. So I'm going to clean up the x to the fourth like term, so I'll have x to the fourth plus 9x squared plus 8x all over the quantity x squared plus 3 squared. It's pretty typical to leave your answer in that form. If you noticed that the numerator could be factored, and that would be helpful in reducing the denominator, so if it would have been helpful for me to take an x out of the numerator and then reduce it with an x in the denominator, I might do that. But there's no benefit to me to doing that right now, so I'm just going to leave it like this. All right, find the locations of horizontal and vertical tangents. Now, Kelsey asked this question yesterday, and I kind of asked her to think about it, but hold off on what the answer to that would be. A horizontal tangent is where your graph, the curve, is instantaneously flat, just for a moment. A vertical tangent is where your graph is instantaneously, momentarily, straight up and down, vertical. So to find a horizontal tangent yesterday, we learned that we set the derivative equal to 0, because a horizontal tangent is the same as having a 0 slope. For a vertical tangent, what should we set the derivative equal to? Well, what kind of slope does vertical have? And don't say undefined. Okay, it has infinite slope. So we want to set the derivative equal to infinity. That might blow your mind a little bit, like how do you set something equal to infinity? Okay, well, never fear, I'm going to show you how to do that. So first of all, let's find the derivative. So q prime. My quotient rule says to start with the denominator, x plus 3, and then to find the derivative of the numerator, so 2x for the power rule minus 4 minus the quantity x squared minus 4x, and the derivative of the denominator, which is 1. The whole thing over x plus 3 as a quantity squared. So we want to clean this up. So I'm going to have 2x squared minus 4x plus 6x minus 12, that's the FOIL, minus the distributing, so x squared plus 4x, the whole thing over x plus 3 quantity squared. So combining like terms, q prime of x would be equal to x squared is the like term, and then I've got a plus 4x and a minus 4x, so I'll have a 6x and a minus 12. The whole thing over x plus 3 quantity squared. All right, to find horizontal tangents, I want to set q prime equal to 0. So that would be setting x squared plus 6x minus 12 over x plus 3 quantity squared, setting that equal to 0. Now I always say, always set it to 0 over 1. The reason I say set it equal to 0 over 1 is because then I can cross multiply. And I'm going to cross multiply that way and this way. And when I cross multiply, x squared plus 6x minus 12 times 1, and then the denominator cross multiplied, I get 0. And that becomes a much simpler problem for you as a calculus student to solve. If you can factor it, great. If you can't factor it, you'll need to use the quadratic formula. Okay. For 12, we've got 1 and 12, 6 and 2, 3 and 4. None of that works, so we're going to need the quadratic formula. So x is negative 6 plus or minus the square root of 36 minus 4 times a times c, so negative 12 all over 2a. So negative 6 plus or minus 36 plus 48, which is 84, all over 2. Now 84 can be simplified and broken down. So negative 6 plus or minus 2 rad 21 over 2. So negative 3 reduced, I'm just reducing, plus or minus the square root of 21. Okay, so what does that all mean? At the x values of negative 3 plus or minus the square root of 21, my original function would be momentarily flat. You wouldn't even hardly be able to see that it was flat, but it would have a horizontal tangent at those places. All right, now we want vertical tangents. So for vertical tangents, we're going to set q prime equal to infinity. So that's x squared plus 6x minus 12 over x plus 3 quantities squared set equal to infinity. Now there's a better way to write infinity. Infinity is 1 over 0. It's the reciprocal of 0. That's the definition of infinity, the undefined number. So then I'm going to cross multiply these. This time, when I cross multiply, I'm going to get x plus 3 quantities squared equals 0, which means x plus 3 is equal to 0, and x is negative 3. So that tells me that I have a vertical tangent where this graph is momentarily straight up and down with an infinite slope at the x value of negative 3. So I have 2 places of horizontal tangency and 1 place of a vertical tangent. All right, last example. We're going to put everything together using all the rules. Suppose that u and v are differentiable. That means that they are functions. It means that they were continuous, because if they're differentiable, they have no corners, no cusps, no vertical tangents, and no points of discontinuity. So if they're differentiable, they must be continuous. If they're continuous, they must pass the vertical line test, because these are functions. So we know all of that just from that statement. And suppose that 5, 7 is on the u graph, 5, 2 is on the v graph, and the slope on the u graph is negative 3, and the slope on the v graph is positive 6. Now, do we know what these functions look like? No. Do we know what these functions' equations are? No. Do we need to? No. Because we're going to follow the rules. The first question is asking us to find the derivative using the quotient rule. Now the biggest mistake I see at this point is going to numbers too quickly. Rules first, numbers at the end. So my rule first is v times u prime minus u times v prime over v quantity squared. Okay, go with your rule first. Then put the numbers in. If you did it backwards, if you put your numbers in first, if you just went to u over v and you put 7 in for u and you put 2 in for v, you'd get 7 over 2, and the derivative of 7 over 2 would be 0. And your answer would be 0. And that would be 0 every single time because you would start with numbers and the derivative of numbers is 0. So we don't want to start with numbers. We start with the rule. And once we have our rule worked out, then we're going to plug the numbers in to help us figure out the value. So now I'm going to put in the values. The value of v, and all of these are based on 5, right? They all had 5 in common. But the values are all different. So the value of v is 2. The value of u prime is -3. The value of u is 7. The value of v prime is 6. All over the value of v, which is 2. So I have -6 minus 42 over 4, -48 over 4, so the answer is -12. For part B, again, I'm going to use the rule first, the numbers second. The rules first with the numbers 10 and then u and v as a product. Remember, 10 is a constant. The constant can get pulled in front of your derivative. So this becomes first 10 times the derivative of uv. So that would be 10 times, and then we do the product rule for our rule now. And our product rule starts with u and multiplies by v prime, and then switches to v multiplied by u prime. So I'll still have 10 in front, and now I can put all the values in. And the value of u is 7. The value of v prime is 6. The value of v is 2, and the value of u prime is -3. So I'm looking at 10 times 42 minus 6. That's 10 times 36, or 360. All right, so you've been introduced to 6 total rules so far. A constant rule, a constant multiplier rule, the power rule, adding and subtracting, and then now the product and the quotient rule. So you've got all the building blocks of the rules that you need to work with the different polynomial and rational functions. All right, good luck with this, and we'll talk more about this next time.